Okay, and hello everybody. This is solving stuff with Sosa. Okay, so we are in the last topic of Unit 4, which is electricity and magnetism. So I'm going to be recording this video that has to do with the last topic, which is about inductance. Okay, and so let's get to it. Inductance. Remember the mighty Thor, the god of thunder, Thor? We talked about this at the beginning of the semester. Always respect and remember the god of thunder, the almighty Thor. So remember that we talked about Thor. Remember Thor. We've got Mjolnir here. It's a heavy hammer. It's heavy. So we talked about Thor at the beginning of the semester. So we talked about resist Thor. That's the Avenger who blocks the path. It opposes the flow of current. Then in unit 2, resist Thor was unit 3. In unit 2, we talked about capacitor. That's the Avenger who absorbs and stores energy. Now we're going to be talking about inductor. And basically, inductor has to do with what we've been talking about up to this point relating to magnetism and coils and being able to create a magnetic field that has to do with the flow of current. And the last one, which is transistor, we're going to talk about him next semester in industrial electronics. This is a heavy hammer. I'm going to put Mignola over here. Okay, so the inductor. An inductor is rounding out the passive elements that we're talking about that have to do with electrical circuits. We first talked about the capacitor that stores energy. Then we talked about the resistor that opposes the flow of current. Now we're going to be talking about the inductor. The inductor is the next passive element. Why are these passive elements? These are not going to generate energy. They're going to be absorbing energy. And basically an inductor is generated by a coil. Okay. So remember that if we have a coil and that coil has current going through it, we're going to generate a magnetic field. So that relationship that has to do with the coil and the magnetic field, there are properties related to that. And that element, that component is called an inductor. So how we define it, it's this passive electrical component that consists of a coil of wire. I'm going to see that there's other elements there like a core that takes advantage of this relationship between electricity and magnetism and the flow of current and everything we've been talked about up to this point about current creating magnetism, magnetism creating current, etc. This is a simple circuit where we have a coil there. Now, inductance is the measure or is a measure or the way we measure an inductor. So we talked about a capacitor is a component, the element. Capacitance is the measure of how much energy a capacitor can store per unit charge. Then we talked about a resistor. Resistor was the element, and resistance was this measure of the opposition to the flow of current. So the inductor is the element, the component, and inductance is going to be a measure of the energy, magnetic energy, an inductor or a coil can store based upon the magnetic field that's created by the flow of current. It's also a measure, or has to do or is related to the opposition of the rate of change of electrical current through a coil. Now this is important because the resistor is the opposition to the flow of current, like a restriction in a tube. The inductor or inductance is a measure of the opposition of the rate of change. So current is going in one direction, but if current increases or decreases, or goes from one direction to the other, the rate of change is going to be the energy that can be created by that rate of change. Inductance has to do with that. And remember one thing, magnetism is created by the movement, okay? So the current that's moving through a coil is going to generate a magnetic field. Magnetic field, if we move a conductor through it, is going to induce a current. And so everything has to do with movement. So that's why we're talking about a rate of change. We see the symbol there for the inductor or an inductance is a coil. So it's like a bobbly line there that we have there. That's the symbol. And inductance is represented by an L. Okay. The units are henries. They're called henries. And a henry is 1 Weber per ampere, per amp. So it's a measure of the kind of like a measure of the magnetic flux by unit of current. Okay. These are just some symbols for the inductor. The typical inductor is just this sort of like windy coil that we have here, this one. A core that has, an inductor that has an iron core, because an inductor has different components. So one is the coil itself, but the coil isn't like floating around. It has to have some sort of core in it that holds the coil together, which is this element that we have here. So if we've got an iron core, this is the element. If there's a ferrite core, different materials. Remember that we talked about when we have a component and there's an arrow going through it, that means that the component is variable. A capacitor or resistor symbol that has an arrow going through it, that means that it is variable, okay? And this is an example of how an inductor or coil would look. And basically, we've got current going through the coil. The coil is held together. I'm sorry, but it's really late. I'm recording this video really late. Not really late, but a little bit late. And so I'm very sleepy. It's been a long week. It's been a long month. It's been a long first half of the year. It's been a long pandemic, kids. The current is going through the coil. The coil is held by the core. And some important things here is that, remember that the strength of the magnetic field is going to be related to the length of the coil and the current going through it. So remember that we do a coil because the length of the can be reduced if we wind it around. So the number of turns of the coil is going to be important in the inductance and inductor relationships that we're going to be talking about. And so an inductor coil, it's an inductor or an inductor coil, is going to have a core. The core is going to have a certain cross-sectional area. And there's going to be a number of winds or turns of the wire per unit length that are going to go through the coil. So the number of coils and the current going through it is going to be related to the magnetic flux that's going to be generated. And so it's going to be directly proportional. There's going to be a relationship through that. So the more turns, the stronger the magnetic flux can be created for a particular current that's going through it. And so if we have a coil and we have the voltage or applier voltage, there is going to be the change in the magnetic flux is going to be, there's going to be a proportionality. That proportionality is going to be given by the turns. And we can substitute some values here where we substitute and leave everything with regards to the cross-sectional area and the length of the wire and the permeability of the materials, and multiply that by the differential in current. And these factors that are here that have to do, I'm pointing with the arrow, and I don't know if you're seeing, these relationship that we have here that has to do with the area, the length, the number of turns, and the permeability, that's going to be inductance. So Remember when we talked about capacitance and we said, what are the factors that affect the capacitance? Well, the cross-sectional area, the distance between the plaques and the material, the dielectric material, those three factors. Then we're talking about resistance. The resistance in a wire, what are the factors that affect the resistance? Well, the length, the cross-sectional area, and the resistivity. What are the factors that are going to affect inductance? Well, the cross-sectional area, the length of the wire, the number of turns, and the permeability. Those are the factors that are going to affect inductance, which is this property, the measure of the energy, magnetic energy that a coil can store. Now, this is the easy part, because we just have to remember and kind of extrapolate something that we already know. What happens when we connect inductors in series? Well, sorry about the yawn. The yawn give me energy to finish strong. Well, spoilers, guys. Inductors in series behave exactly like resistors in series. Spoiler, again. Inductors in parallel behave exactly the same way a resistor in parallel works. Actually, inductors and resistors have this sort of weird relationship with regards to current. Let's say that resistors have a certain effect on current when it's direct current, and when there's alternating current, that's where inductors come into play or have some effect there. We're going to see that in the next course. However, if I have inductors in series, for example, how I have them there, I've got the inductance. There's a current going through the inductors, and there's voltages in each conductor. Now, the current going through the conductors has to be the same because it's in series. That still applies. And we know that the inductance multiplied by the differential of current times time, or the change in current, remember the rate of change is a derivative, is the voltage. And if I add all of the voltages, I have a total voltage, which is the voltage that I'm providing the whole circuit. Well, actually, in this expression, these can be eliminated because the current is the same. And what am I left with? I'm left with this expression. So the total inductance of inductors connected in series is simply going to be the sum of the inductors. Exactly the same as a resistor. Exactly the same as a resistor. Remember that. Inductors behave exactly the same way as resistors with regards to series and parallel. So, very complicated example and exercise. I've got 3 inductors. Oh, I'm so tired. 3 inductors, 10 millihenries, 40 millihenries, and 50 millihenries are connected in series. What is the total inductance? It's going to be the sum of the 3 inductors. I've got 3 inductors inductances or inductors connected in series. The total inductance is going to be the sum of the 3 inductances. So 10 plus 40 plus 50 is 100 millihenries. Same behavior as a resistor. Parallel. Parallel inductors behave exactly the same as parallel resistors, like we've already seen. So now I've got a parallel circuit. I've got 3 inductors connected in parallel. I've got a voltage going across the inductors. It's called VAB. We know, because it's a parallel connection, that the voltage in 1 and the voltage in 2 and the voltage in 3, all of these have to be the same and the same as the total voltage, which is exactly what we have here. And we know that the voltage for an inductor is the inductance multiplied by the rate of change of the current. Okay. And so if we substitute that here in this expression, the expression of the sum of the voltages, then we're going to have the total voltage is going to be equal to the total resistance, total inductance, multiplied by the differential of the current of each current going through the derivative of the current time with regards to time, which is the rate of change of each current. But we already said that the voltages are the same. So the total voltage is going to be the inductance divided by the voltage times the each inductance. These can be eliminated. Okay. And in the end, we're going to have a similar relationship to the one we had with resistors. So the reciprocal of the total inductance is going to be the sum of the reciprocals of each inductance, behaving exactly the same as resistors in parallel. So let's assume that we've got now 3 inductors, 60 millihenries, 120 millihenries, and 75 millihenries connected together in parallel. What would be the total inductance? Well, the total inductance, the reciprocal of the total inductance is going to be the sum of the reciprocals of each individual inductance. And so the reciprocal of the total inductance is going to be equal to the reciprocal of the sum of the reciprocals of each inductance. So we substitute that here. We invert it and we get 26 millihenries. Again, inductors in parallel, total inductance behaves exactly as resistors in parallel and equivalent resistance. Okay. Let's add some complication here to this. Now let's try to find the equivalent inductance of the following inductive circuit. Darn. Well, almost done. We are going to take the same approach we did with resistive circuits. And I'm going to kind of walk through it. I'm going to use different colors. First off, I'm going to use a variety of colors here. I'm going to start off with L6 and L7. Let's do it like this were like Blue's Clues. Okay, kids. The 2 inductors that I marked in blue, are they connected in series or are they connected in parallel? You're right, they're connected in series. How do I know that they're connected in series? If I try to identify current going through these, if I go from L6 to L7 or L7 to L6, there's no interruption to the current going through one and the other. Whoops. There's no interruption or separation of the current. That's why they're in series. Once I have those 2 in series, how are they connected with regards to L5? They're connected in parallel. This array of these 2 is connected in parallel with L5. How would that be connected with L4? The combination of these 2 connected with L4 would be in series. And how would that array be connected with L3? You guessed it, that combination is in parallel. I need to move my window here. Next up, how would that one be connected with L2? It would be connected in series. And lastly, how would everything be connected to L1? It would be connected in parallel. Okay. Now I'm going to do something because maybe this is really confusing. So what I'm actually going to do, I'm gonna walk through that. Okay. Let's do each of those steps, just so we have that sort of explanation. Oh, I actually have a blank slide to do that. I was finding a blank slide to do that, but I actually have that. This is a mess. Let's try to do this step by step, okay? I'm going to clear these drawings. And let's go to the next step here. Okay, so the first step is that I'm going to do this in colors again. I'm going to join these two, and I'm going to call that L6, 7. Okay, so the new circuit, I'm going to go from left to right. The new circuit would be my drawings are really ugly. I asked for feedback to some students of this semester, and they told me, oh, the class was pretty good, but your drawings and your writing are terrible. Work on that, please, professor. And they are right. They are correct. I'm not going to write down the names again, but this inductor here, this would be L67. I'm going to write the numbers, or else there's going to be confusion. This is L5. This is L4. This is L3. This is L2. And this is L1. Now we're going to do, I don't remember what colors I used in the previous one, but I'll do it here. We are going to do these two. Okay. And those two are in parallel. And I'm going to call this one L6, 7. I'm putting the numbers in the order that I'm doing the reduction. That's why it's 6, 7, 5. And that would give me something like this. I'm going to draw that in orange. Oh, that is too ugly. Come on, George. Come on, Sosa. This would be L6, 7, 5. Okay. This is L4. This is L3. And if you don't understand my writing, tough. And now we're going to take these two and we're going to call this one L6, 7, 5, 4. Okay. I forgot to say something here. I'm gonna mark these. This is series. This is parallel. This is series. I'm not going to do the calculations. By the way, I'm just going to do the procedure. Then we go over here and I'm going to have boom, 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 boom. Boom, 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 boom. Really detest writing with the mouse. Be patient. Remember, you can fast forward all of this. Different from a class, since this is being recorded, you can just fast forward it. And this one would be the one we've got here. That's L6, 7, 5, 4. And now we're going to take these two, I don't have to exaggerate it that much, these two, and we're going to call this one L6, 7, 5, 4, 3. And this is a parallel, right? Almost done. And that is going to give us, boom, 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 L2, boom, 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 what the heck? Boom, 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 boom. That's going to give us, let me write down the names here. We're almost done, almost done. L2, L1. We're kind of going to use their, I don't know, let's use another tone of blue. Oh, let's write this one down here. This is going to be this one here. This is L6, 7, 5, 4, 3. We're almost done here. Let me use another tone of green. Now let me use another, which one could we use? Let me use another brown here. These two would be called L6, 7, 5, 4, 3, 2, and this would be in series. And lastly, we would have we would be left here with L1, and we would have over here this brown one. God, the thing is that I try to write small, and that really does not help things. This one here, and this one be L6, 7, 5, 4, 4, 3, 2. So ugly. Sorry about that. It is late. And lastly, these two, which I'm just going to call LT, is the total resistance, total inductance, I'm sorry, and these would be in parallel. And that would be kind of the procedure of result. I'm not doing the calculations, just kind of identifying how we would go about the reduction. The important thing here is that if we have a series, we'd add them. If it's a parallel, we'd the reciprocal of that array would be the sum of the reciprocals of these. And basically, this would be kind of the procedure to reduce it. What we've got in the next slide is we've got kind of the explanation of this with the calculation. So here's kind of inductor L5 is in parallel with inductors L6 and 7. Then the second inductor L3 is in parallel with inductors L4 and LA. And each of these is given a name. They're doing kind of a combination here, and in the end, we get 15 millihenries. Okay, that would be the complete inductance procedure. And so the thing to remember here is that, again, inductance is inductors in series and in parallel behave very similarly to, or almost exactly, actually, to resistors. In series and parallel, inductors behave the same as series, resistors in series and parallel, okay? Okay, that's it, or at least that's what we're going to talk about up to now with regards to inductance.